This webcast talks about energy transfer and energy conservation diagrams. When a system is isolated, that means that there are no interactions with other external systems. So there's no opportunity for energy to either be added or removed from the system. So the total energy is constant. That means that delta E, the change in energy, is zero. But energy can be redistributed within the system. So the total amount of energy doesn't change, but the way it's stored can change. We've seen that. For example, the simple example of a ball that initially is being held at some height, so it has gravitational energy. Once you let it begin to fall, that gravitational energy moves into kinetic energy. So the change in internal energy of a system equals the changes of the energy in the various storage modes. And you could represent that by this equation, that the change in energy is the change of kinetic energy plus the change of gravitational potential energy, and so on. But all of those changes have to add up to zero. This may look like a complicated formula, but think about it. What that means is that, in that ball that's being dropped, if there's a change in gravitational energy, the gravitational energy is getting smaller as the ball falls, well, that energy has to go somewhere else within the system, and it's moving into the kinetic energy storage mode. Now, when a system does have interactions with a different external system, it's possible for energy to move from one system to another. So when these interactions occur, the system is no longer isolated, and so its energy could either grow or it could shrink, it could get smaller. If we were using a pie chart to represent the energy stored in a system, then the size of the pie might change, right? It could get bigger or it could get smaller. There are three possible ways for energy to be transferred across a system boundary. The first method is called working. Working is a process by which energy transfers because a force gets applied and causes a displacement. And working is the primary method of energy transfer that we're going to be using in our class. But there are two other mechanisms. One is heating, which is represented by a Q. Heating is a process in which energy transfers from one system to another because there are differences in temperature. Energy always flows from the hotter system to the colder system. And then the third process is called radiating. That's a process in which energy flows from one system to another by photons or electromagnetic waves. Think of our sun. The sun radiates a lot of energy in photons and electromagnetic waves, and some of that energy gets absorbed by the Earth's system. So working is the primary mechanism that we'll be considering. Work is an amount of energy that flows into or out of a system. Work is a way of transferring energy. And only systems that can contain energy are able to perform work. And they perform work by applying a force on another system. The forces themselves are not systems. The force does not contain any of the energy. It's just a way to help transfer the energy. So now that we're talking about systems that can interact with other systems, we need to kind of update our energy conservation equation. We know energy can't be created or destroyed, and the total energy of an isolated system remains constant. So if the energy in the system changes, we know it was not isolated. There must have been an energy transfer by working or heating or radiating, because those are the three mechanisms that allow energy to be transferred. We could represent this with this equation that says the change in energy is still going to equal the sum of all of this energy storage modes, right? The kinetic energy, plus the gravitational energy, plus the elastic potential energy, plus the dissipated energy, all of those changes. And if those changes don't add up to zero, then they must equal the sum of all of the energy transfer mechanisms working and heating and radiating. Now, for mechanical problems, which are the type of situations that we're looking at, the only mechanism for transferring energy across the system is by external forces, and that's called working. And so this equation kind of simplifies to saying if there's a change in energy, then it must equal the amount of work that was done. Okay, so we're going to begin using a new type of graph, or to help visualize the changes in energy. It's called an energy conservation diagram, and this is a really nice tool to visualize how energy gets redistributed within a system, or if there are transfers of energy into or out of the system, how those transfers are occurring. And so to start with, I just wanted to give a very simple example and show a comparison of both the pie chart, which is a tool we've been using, to this energy conservation diagram. Okay, so let's just look at the example of a ball that is initially held motionless above the ground, and then it's allowed to drop. So it speeds up as it falls down to the ground. And we're going to look at it at position B just before it hits the ground. So it's moving very fast, and its height is almost zero. If we represented this with an energy pie chart, it would look like what we've got here in the lower left-hand corner. At position A, all of the energy is stored as gravitational potential energy. At position B, all of the energy is now stored as kinetic energy, because it essentially has no more gravitational energy. It's almost on the ground, and it's moving fast as it falls down. So it's all kinetic energy. Okay, on the right, we see an energy conservation diagram. Notice that there are 4 parts to this diagram. In the center, what I've labeled part A, there's a circle. That's where you list all of the things that are part of the system. So in our system, we've got the ball and the earth. Then on the left-hand side, in part B, we have a bar chart. This bar chart shows how the energy is distributed at position A. At position A, the ball was being held motionless above the ground, and so all of its energy was stored as gravitational potential energy. On the right-hand side of the conservation diagram, we have another bar chart. I've labeled that C. This is the bar chart showing how the energy is distributed at position B. So for this example, at position B, all of the energy is stored as kinetic energy. Then below below A, B, and C, there's a final box, and I've labeled that D. This is where we write the energy conservation equation. Basically, we're saying that all of the energy on the left-hand side of this graph has to equal all of the energy on the right-hand side of this graph, because the initial energies were all stored as gravitational energy. The final energies were all stored as kinetic energy. The change in the gravitational energy, in this case, has to equal the change in the kinetic energy. Okay, let's just talk through that organization one more time. You look in the center first. In that circle, you list everything that is part of the physical system. In other words, you're drawing the boundaries around what you're considering to be part of the system. In the upper left corner at B, there's a bar chart that shows how the energy in that system is distributed at position A. In the bar chart on the upper right, what's labeled C here, you have a bar chart that shows how the energy is distributed at position B. And then below all of these bar charts, there's a box where you write the energy conservation equation. The boundaries around the system are somewhat arbitrary. I mean, different people, or for different situations, you may identify or define these boundaries differently. For our purposes, usually our problems will explicitly state, it'll say something like, consider the system to include, and then it will tell you what you should list in that circle as part of the system. The choice of the system will affect how the problem is analyzed. It's important to remember energy can't exist on its own. It has to belong to some physical system. So for example, if you don't have in your system, if your system doesn't have a spring or something else that can perform an elastic deformation, then your system cannot store elastic potential energy. It's recommended that you always include the Earth in the system so that if there are changes in height, we can talk about how the gravitational potential energy, E sub g, changes. And that way we can think about gravitational potential energy as an internal energy rather than thinking about, oh, that's work that's being done by the Earth system on our system. So when we start to create an energy conservation diagram, the first step is to identify what you're considering to be the system. List that in the circle in the middle. The second step is to identify how the energy is stored at position A. Then identify how the energy is stored at position B. And finally, if there are any energy transfers that are happening because your system is interacting with other external systems, then you need to identify the mechanism. Was it working, heating, or radiating, and then show how that energy transfer was happening. Let's look at a detailed example, and I'm going to look at it 3 different ways to show you how the choice of boundary of the system can affect how the problem is analyzed. The situation is the same, exactly the same in all 3 parts of this example. It's just that the way that we are thinking about how the energy is distributed and transferring depends on what we consider to be the boundaries of our system. Okay, so the basic situation is we have a person pulling a box with a rope. They're pulling it along a rough surface at a constant velocity. Okay, because they're telling me it's a rough surface, I know there's some friction between the box and the floor. Okay, so in the first view here, I'm going to consider the system to include everything that I'm looking at. The person, the box, and the ground. All of that is part of the system in part A here. Okay. So when I do an energy conservation diagram, first I list those things in the center circle. The person, the box, and the ground. Then on the left-hand side, I fill out the bar graph. The person is storing chemical energy. Right? We don't use chemical energy in many of our examples, but a person, their internal energy is stored as chemical energy. The box is moving, and so there's kinetic energy stored in the box. Remember, we never show dissipated energy in the first view, so I haven't seen the box move any distance yet, so I am not yet showing any energy that's in the dissipated category. Okay, so that's the way the energy is distributed at the beginning in position A. Then I think about position B being when the box has been pulled and it's moved across the room. Okay, so the person has used some of their chemical energy to move this box. So the person has less chemical energy now. The kinetic energy of the box is still the same because we said in the description that the the velocity of the box is constant. So the kinetic energy is constant. But as the box moved across the floor, the rough surface of the floor, there was friction. And so the atoms and molecules on the surface of the box and on the surface of the floor, they have warmed up. They are moving and vibrating a little bit faster. You know, that microscopic kinetic energy. And so I know that there is some dissipated energy. For this example, I am differentiating between the dissipated energy in the box and the dissipated energy in the floor. They are both part of my system, so really the sum of those is, E dis, but I'm just differentiating them in this particular example. Typically we would just have one category for E dis for this example. Okay, and then finally I write an energy conservation equation in the box at the bottom. And so I look at all of the energies in the original state. I had the E chemical energy sub 1, right, plus the kinetic energy in the first state. That was all of the energy at the beginning. That has to equal all of the energy at the end, which is the E chemical 2 plus E kinetic 2 plus the change in the dissipated energy. Notice that when I have the same category, for example, chemical energy, on both the left and the right, I need to use a subscript, for example, 1 and 2, to differentiate what was the amount at the beginning and what's the amount at the end. When the type of energy only appears on one side, I could just talk about the change in that type of energy, like I did here with E dis. Okay, so in this situation, if you count the number of boxes of energy, so you'll see that I have the same amount of energy on the left-hand side as I do on the right-hand side. So there were a total of about 5 boxes tall of energy on the left, right? 4 of them were chemical energy, the way I drew it. 1 of them was kinetic. And now I have about 5 boxes high of energy on the right as well. There's 1 chemical, 1 kinetic, 1.5 each of the dissipated for the box and the floor. So the height, if you put all of those boxes on top of each other, the height of the energy on the left would equal the height of the energy on the right. I mean, this is just descriptive. At this point, I have not calculated these energies, but I'm trying to show that the total energy in the initial state equals the total energy in the final state. This was an isolated system. There were no transfers of energy into or out of the system, and so the total energy has to be the same at the beginning and at the end. Okay. Now, let's look at the same example, but we're just going to change what we consider to be the system. Now, we're only going to have the system include the box and the ground. In other words, the person is now not part of our system. Okay, so look how the energy conservation diagram has changed. Now, there is no more chemical energy in either the initial or final state. The box and the ground cannot store chemical energy. It did not change the actual situation. The person is still pulling the box. The person's applying a force that and uses some of their energy to make the box move. In other words, the person is transferring some of their energy into the system that has the box and the ground. And so we see a transfer of energy into our system. That's the arrow that's coming into the circle that has a W next to it. That's because the energy was being transferred by the process of working. Okay, and so when we look at the energy conservation equation, initially I just had some kinetic energy. That was EK1, and that energy was added to the work that was done on the box. And that amount of energy that was at the beginning now equals the final energy of the box ground system, which is the kinetic energy, EK2, plus the change in the dissipated energy. Okay, and let's look at this example in one more way. This time, the only thing that's going to be part of the system is the box alone. The person is not part of the system, and the ground, or the earth, is not part of the system. Okay, so our system only has the box. So the energy in the box at the beginning is just kinetic energy. It's sliding. And at the end, it's still sliding at the same speed, and so its kinetic energy is the same. But now that it has moved for some distance over the rough floor, the surface of the box that was pressing against the floor is now warmed up. It has that dissipated energy. The floor also got warmed up by the friction. And so where did that energy in the floor come from? It came from our box system. The box applied a force of friction to the floor and transferred energy to the floor by the process of heating. That's the Q, that's an arrow going out of our system, because we actually our box transferred some of its energy to the system that had the floor. And of course the person is still in this situation. The person is the reason the box moved, and so the person was applying a force to the box, causing it to move. The person did work on the box and transferred energy into the box system. So in this situation, we actually have two arrows. One arrow showing energy being transferred into the system. That's the work that was done by the person. And another arrow showing energy being transferred out of the system. That was the heating that our system did to transfer energy to the floor. When we write the energy conservation equation, we have that the energy on the left-hand side of this diagram, which was the initial kinetic energy plus the work that was done, equals the energy on the right-hand side, which is the final kinetic energy plus the change in the dissipated energy plus that Q. Okay, thank you.